Dimensionality reduction. So suppose you're interested in learning what impacts poverty levels, as we talked about, and in that case, this is going to be our dependent or outcome variable, poverty levels in US states. And then you have data on state GDP, median household income, educational attainment, taxes, money spent on education, many other variables that you think can help you predict or understand poverty levels. And all of these other variables, all these other dimensions, all these other features, these other variables, dimension is another word for features or variables. These are the independent or input variables. But maybe you are asking yourself, how many variables really are sufficient to explain the poverty levels? And what are the relationships between the input variables? So sometimes when we're creating a model, as we're going to see later in the semester when we're talking about regression, you want your independent variables, your input variables, to not be correlated to each other, because that screws up your estimation of the dependent variable. Okay, so it's a little tricky and it's kind of difficult because, you know, a lot of these things are related to each other. So it's kind of hard to have independent variables that are not co-related to themselves. So that's a kind of a question that may come up. Are some variables not useful for including in the model? That is, do they introduce some noise? Do they maybe you think they explain something, but they don't? So how do you address this issue of having a lot of dimensions, a lot of variables to explain something? What do you do? Well, there's two ways to do this, and this kind of activity is called dimensionality reduction. So by reducing the dimensions of your feature space, that is of your set of features, your set of variables, you have fewer relationships between variables to consider, and you're less likely to overfit your model. That is, include too many things in the model that may be useful for a particular case, but it's not going to generalize well. So reducing the dimension of the feature space is called dimensionality reduction. There are many ways to achieve this, but most techniques are one of two classes: feature elimination and feature extraction. Now you can look into this from this article over here. The textbook takes a little bit of a different approach, but I think this one is simpler, and we'll focus on these two broad approaches here. So feature elimination. Well, pretty straightforwardly, feature elimination is dropping the variables that you do not think are valuable. Now, an issue is that the variable may have some importance that we did not consider, because you're just dropping completely, so you can't use that, you're not using that feature, so you can't learn from those measurements. And actually, we may learn about feature elimination from that exploratory correlation matrix that we did. So we can see here, let's say we're concerned about poverty percent, poverty level. You can see that some of these measures are related to it. So median household income is definitely, well, not definitely, but looks correlated. It's a very high correlation, 0.7 with poverty percent. And that makes sense once again, because poverty percent is related to median household income. It's based on that number. The total number of people in poverty is related to it as well, but total taxes actually looks like it's not. So maybe we say, oh, this is very weak correlation, so we don't need to include this in our model as an explanation of poverty levels. Total taxes doesn't seem correlated with poverty percent. It's slightly negative, but it's very low, so it's not a factor. So we may go around and start eliminating this. Maybe we need to eliminate this variable from our, if we want to create a model to explain percent poverty levels of poverty in US states. Same here for population. Population, the higher the population, not necessarily the higher the poverty percent. Okay, not related. Maybe you need to drop it. Same thing for tax, for GDP, and maybe also GDP as well. None of these variables actually look correlated with poverty percent. So we can maybe drop these, and that's a way to reduce our dimensions. Now, in this case, we only had a few variables, but often, especially in data analytics, we're going to have lots of other variables maybe hundreds, maybe thousands of variables. So it's good to reduce and remove the ones we don't think are related to our dependent or outcome variable of interest. Now, another approach is called feature extraction. So feature extraction is calculating or aggregating existing features to create new features. Once again, same word, different word for the same thing: features, variables, dimensions. And one that the textbook discusses, a very common one, and one that I will just mention here briefly, is principal component analysis. Principal component analysis is a little bit tricky, and I'm going to try my best to simplify it over here. But generally, it consists of determining the features that are most relevant in a data set by eliminating redundant data points. So a lot of times there will be like redundant data points that in all of the attributes that we're looking in that don't help predict the outcome variable. So we can kind of go around and eliminating them. It does this by calculating how variables are related to each other and aggregating those that move in the same direction. Okay, that is usually like the predictive variables or the independent variables. So let's take a look at this example here that I got from the site Setosa, which I think is simple and maybe helps us understand principal component analysis. So the diagram here shows us the foods that are eaten across different countries. And what we're interested in is to see how these countries are different to each other in regards to the foods they consume. Okay, so there's England, there's North Ireland, there's Scotland, and there is Wales. And at one time I thought this was all the same country, but I've learned that these are all different countries. So let's assume it as such. Four different countries here. And if you kind of look at it, it's not really clear. Maybe it looks a little bit like North Ireland actually consumes less alcohol than the other countries. A bit surprising, right? Maybe, but the other things kind of look kind of similar. Maybe soft drinks, more in Scotland, a little bit less in Wales. But it's kind of difficult to know exactly how which of these variables here, which of these dimensions, which of these foods actually best explain the differences across the countries. Is it really the soft drinks, or is it really just the alcoholic drinks? So what principal component analysis does is integrate some of these that are more predictive than others. Okay, and once you do that analysis, which I'm not going to show here, I'm just showing the result. Once again, this is coming from the site here, Setosa. And once you do, you can determine, first of all, you can determine how many principal components you calculate, so 1 or 2 or 3 or 4. And once you get the first one, you actually already see that there's some North Ireland is all the way over here, and then Wales and England, Scotland are closer together all the way on the left side. So once again, this is the aggregated sort of set of dimensions into one principal component. And you're like, whoa, North Ireland does seem to be different than the other 3, much more than the other 3. So what we're learning here is that Northern Ireland is quite substantially different than the other 3 in terms of the foods they consume, although it's not really clear just by looking at this data set here. And you can start adding more dimensions. You can add 2, and you can also add 3. Above 2 dimensions, it's very difficult to visualize on a 2-dimensional plane. But you can sometimes add like a 3rd dimension here and do that. But and actually that site has some interesting data on this. But if you see, even when we add a 2nd principal component, a 2nd aggregation of relevant or similar variables, we see that Northern Ireland is all the way over here, and then Wales, England, and Scotland are apart, but kind of closer together. So you may be thinking, well, why is it? Well, in one way, you can see, yeah, the alcoholic drink, as we said before, is pretty different in Northern Ireland compared to the other 3. The other 3 are much more together. But also, if you kind of look, you can see fresh fruit is also very much different in Northern Ireland compared to the other 3. So the other 3 are around 100, 1,000 rather, and this one in Northern Ireland is around 67, and also fresh potatoes too. So all these three variables kind of really show that Northern Ireland is pretty different than the other three, and maybe all the other variables. So what's the principal component analysis doing is maybe taking these three variables and emphasizing them to show you the difference across these countries, these four countries. Now, the thing is, we don't really know what variables are actually being selected by the principal component. And that's kind of one of the shortcomings. And because it's just doing all kinds of number calculations to just determine what variables lead in the same direction and how these countries in this case are different to each other. So what variables help predict the differences between the countries? So the thing is, PCA is an exploratory tool only. Notice how we had to kind of go back and forth to understand. We go from the principal component analysis back to the data to better understand where the changes may be coming from. And the aggregated variables are difficult to interpret. So because the outcome of the principal component analysis are these principal components dimensions themselves, this doesn't tell me that, oh, it is potatoes that is just different across Northern Ireland, substantially different than the other countries, or it is soft drinks and so on. So it's good for certain tasks, but not very good for others. And I highly recommend you to take a look farther into these other online resources that I'm citing over here, in addition to the book, for you to better understand principal component analysis. Okay, that's it for this one, and I'll see you next time.